let's look at another example. So we're looking at the series summing from 1 to infinity, terms that look like negative 1 to the n times the square root of n plus 1 minus the square root of n. First off, this looks like it's alternating, but we should double check. So maybe our first question is, what signs are possible for this expression? Well, so if we look at f of x equals the square root of x plus 1 minus the square root of x, since y equals the square root of x is increasing, that tells us that f of x is always going to be greater than 0. So that means that this term is always positive, and so indeed we do have an alternating series because the only thing determining the sign is this term negative 1 to the n. Sweet, so it's alternating. Next up, we should do the divergence test and check to see what is the limit as n goes to infinity of the terms. So we can either look at it where we have this negative 1 to the n term, or we can just take a look at the limit as n goes to infinity of the magnitude. So drop the negative 1 sign. So I'm going to do that second possibility. So I'm dropping the sign. So I just have the square root of n plus 1 minus the square root of n. This is an indeterminate form. It has the form infinity minus infinity. So we're going to multiply top and bottom by the conjugate. So remember, this is a technique we do when we take sums or differences of square roots. It's just for when we have square roots. Okay, so we're multiplying by square root of n plus 1 plus square root of n over square root of n plus 1 plus square root of n. We can simplify this, and we're left with n plus 1 minus n over the square root of n plus 1 plus the square root of n. We simplify, right? You can see that this n and negative n are going to cancel out. So this is the limit as n goes to infinity of 1 over the square root of n plus 1 plus the square root of n. Notice that we haven't actually taken any limits yet. So another way of writing our series is n equals 1 to infinity, negative 1 to the n, times 1 over the square root of n plus 1 plus the square root of n. Okay, now though, we have a form that's not indeterminate. When we take the limit, our denominator is approaching infinity. It's getting very, very big. So its reciprocal is approaching 0. And so we satisfy this second condition that we need for the alternating series test. Finally, we need to check to see if our terms are decreasing in magnitude. And this is pretty easy to check, so why don't we take a look at bn plus 1. This is equal to 1 over the square root of n plus 1 plus 1 plus the square root of n plus 1. And bn is equal to 1 over the square root of n plus 1 plus the square root of n. Okay. We know that the terms in the denominator of bn plus 1 are bigger since the square root function is increasing. And they have the same numerator. Therefore, when we take the reciprocal, therefore the expression bn plus 1 is going to be smaller than bn for all n. We could have also, for example, taken the derivative of the function f of x equals 1 over the square root of x plus 1 plus the square root of x. Right, this isn't too bad, it's just a little chain rule. So we get square root of x plus 1 plus square root of x to the negative power. Our derivative is equal to negative 1 times the square root of x plus 1 plus the square root of x. And then we need to multiply by the derivative of each of these terms in the inside. So this is 1/2 x plus 1 to the negative 1/2 plus 1/2 x to the negative 1/2. You can notice here, though, that this is negative, this term is positive, and so are these terms. These are also greater than 0. So together, our derivative is less than 0. And so our function is decreasing. And so Bn, which is f of n, is going to be greater than Bn plus 1, which is f of n plus 1. Great! Therefore, since we've set aside these three conditions, we can say this series converges by the alternating series test.